Okay. Good afternoon, ladies and gentlemen. Welcome to International Virtual Course on Fundamental and Technology of Advanced Material, Lecture Session 5. Before we begin the lecture session, let us pray together according to our respective belief and allegiance. Let us begin. And finish. Ladies and gentlemen, we would like to take Zoom online photos first. Please open your camera. We are ready to take the photo. Please give your smile. 1, 2, and 3. Okay, once again, page second. One, 2, and 3. Okay. Dear all participants, today's lecture session will be given by Dr.rer.nat Akfiny Hasdi Aimon from Institut Teknologi Bandung. The topic of today's lecture is nanomaterial and beyond. During lecture session, if you have any question, you can ask directly to the lecturer by using raise hand feature, or you can write down your question in the meeting chat and the moderator will read the question. Let us begin lecture session. Please, Dr. Akfiny, you can have your time.
Okay, thank you, Arun, for introducing me to the forum. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Before we start, let me share my screen. Okay. Okay. Have you seen it already?
Yes.
Okay. Okay, Bismillahirrahmanirrahim. Good afternoon, everyone. So today I will give like a lecture for in the coming 2 hours about nanomaterials and beyond. So in this lecture, I would like to give a bit of introduction, or maybe most of you already know about this, which is we will have like an overview about nanomaterial, what is nanomaterials, and then synthesis of nanomaterials, and then how to do characterization, what characterization that we can do for nanomaterials, and then a bit introduction about carbon-based materials, and then exploring beyond of nanomaterials. In this chapter, for exploring beyond nanomaterials, I will highlight some of my research to you, the laboratory research about that. And then the last part of this talk, I will try to elaborate to all of you about the future direction, challenge, and ethical consideration about these nanomaterials. Yeah. Okay, I think most of you maybe already know me. I'm Akfiny Hasdi Aimon. I'm from ITB. I'm one of lecturer in physics department. Yeah. Okay, let's have a look. Okay, now we go to the chapter 1. Oh yeah, for your information, most of this lecture is part of our book. So we try to make books in our research group, or KAKA, which is physics and Fisika and Technology, Advance of Materials. Yeah, technology, yeah, such of that. Oh, okay, sorry, it is a bit crowded here. So from Physics and Technological of Advanced Material Research Group. So the books will be talk about nanomaterials and devices. And my today's lecture will be I will take part of that books, yeah. So in chapter 1 of that books, it will be introduction about nanomaterials, or where the nanomaterials comes from, characteristic and then classification of nanomaterials, and physical principle of nano effects. So what is the difference between nano particles while the materials become in nano size? What is the difference between in nano in bulks? Yeah. Okay. So as you already know before, maybe you quite often see this picture here. Yeah, this is in nanometer scale. This is 1, this is 10, it is 100, 1,000, and it's 10 to the power of 8, which is this is the size of our tennis ball. So you can imagine in nanomaterial size, you can see antibody, glucose, virus, and also liposome is a polymer, dendrite, gold nanoshell, quantum dots, which is, and then fullerenes. This is the size of nanomaterials, yeah. So the terms of nano is derived from a Greek word.
Recording in progress.
Called nanos, meaning dwarf or something very small, yeah. The origin of nanoscales, it starts from the 5th century BC, and then it comes up from Greek philosopher Democritus, yeah. And then early use of nanoparticle we can see from an artist in 19th century. It created similar effect in their picture or pottery, use silver and copper nanoparticles. Yeah, and this is we also see we see in microscopy, and this is the particle of silver and copper from this picture. Yeah. Okay, this is the origin of nanomaterials. Yeah. And then we also know about nanocomposite. Yeah, nanocomposite utilization in ancient artifacts include Listergut cup. Yeah, which is this is where the nanomaterial silver and gold nanoparticle to use in for the coating of this cup. Yeah. And then Michael Faraday in 1857 presented the first report on nanoscale material with synthesis of colloidal solution, which is a gold nanoparticle. Yeah, so gold nanoparticle in solution. And then after that, a significant advancement, which is come from discovery of carbon nanotubes by Professor Ijima in 1991, and development of synthesis method of quantum dots by Mogi Bawendi from MIT in 1992, which is we know that he just get a Nobel Prize in 2023. Yeah, about quantum dots. So, and then the history of nanomaterials also continue in 1959 by Richard Feynman. He said that imagine that if one day atoms and molecules could be arranged as what people want them to be, how different the world might be. There is no doubt that if we could control things on the very tiny scale, the scope of physical properties we can get greatly expanded. So here, from here, we know that the perfect law of nanomaterial is existence is perfect, and only that which is perfect can exist. Yeah. And then which means that nanomaterials have special structure, special shapes, and determined by their atomic arrangement and magic numbers. What is the magic numbers means here that we can see from C60 or C70. It has a highest probability of forming fullerene structure, while for C59 or C71, we cannot find this kind of magnificent structure. Yeah. So for this, they got a Nobel Prize for this finding. Yeah. And we see that from this nanomaterial, they will have a different size, shape, surface, and composition also. Yeah. Okay. So next one. So here is the picture where we can see the difference between nanomaterials and bulk materials. Yeah. So here, this is the bulk form, and this is the nanoparticles. So this is a bulk, and then it has optical properties, electronic properties, and then magnetic properties and mechanical properties. But for nanoparticle that we know there before, which is 10 the power of minus 10, 10 the power of minus 9 meter, we see they have a very unique, so many structure that they can have, and they will have a very diverse optical properties. It can give a diverse color like blue, green, yellow, and red from cadmium sulfide quantum dots. And also for the electronic structure, we see that there will be a difference between bulk materials and nanoparticle. And also their magnetic properties, they will have very unique, and they can be give super paramagnetism properties, and also the mechanical properties of the materials. Yeah, and we will see the detail of these properties in the following slides. Yeah. All right, so this is the nanomaterials. So the classification, there are zero-dimensional, which is nanoparticle. Even quantum dots also belongs to zero-dimensional nanomaterials. And then we have one-dimensional nanomaterials, which can be like a nanotube, nanohorns, or also of fibers. This is belong to one-dimensional materials. And then we have two-dimensional, like a nanosheets, nanolayer, and three-dimensional, which is we have an arrays of nanowire or nanotubes. Yeah. Okay. So here, this is the physical principle of nano effects. The first one is discontinuous electrons level. So as you can see, maybe in your class, in your university, maybe. So here, this is I think everyone already know this is the energy level for conductor material, insulator, and semiconductor. We have here valence band and conduction bands, which is over on top of each other for conduction band. And then for insulator, there is a gap between, and in semiconductor, there is a small gap between valence band and conduction band. But for nanomaterials, so see here, we have a single atom, diatom, polyatom, and solids. And they have a discrete energy level, yeah, for this case, like this. There is a band, and then they have a band, and they have a band gap. And it depends of the atom's arrangement, yeah. So in bulk materials, the energy level merge into a continuous band because they have so many atoms in there, construct from many electrons, and then leading to high conductivity. While in nanoparticles, the energy levels remain discrete due to a limited number of atoms, yeah, resulting in unique magnetic, optical, thermal, and electrical properties. Yeah. So because they have a discrete energy level, they comes with a unique physical and chemical properties. Yeah. All right. So Next, for the nano effects, we know that about the Kubo theory, which is originated in 1950s to describe nanoparticle phenomena using the Kubo formalism. So Kubo theory address the quantum size effect on electron energy levels around the Fermi surface in metal nanoparticles. Yeah, showing that at low temperature, the specific heat of nanoparticles approach zero, differing significantly from bulk metals. Yeah. He also introduced key assumptions about the electronic states of large aggregates of small particles, bridging the gap between theory and experimental observation, despite the challenge of measuring individual nanoparticles. Yeah. The next one is about the quantum size effects. So as we see in this picture, we have different size of particle. Yeah, this is the small one, and then this is the bigger one. To the left, it became bigger. To the right, it becomes smaller. So here, inside of the particle, there is electron wave propagate. And here we see that the size of material inversely affect the distance between energy levels, causing nanometals to transition from a quasi-continuous to discrete electronic energy level as particle size decreases. Yeah. And then when the size of these materials become comparable to the Berkeley wavelength, yeah, the electron wavelength of electron, it restricts the electron motion, leading to discrete energy levels. This quantization of energy level is the hallmark of quantum size effect, profoundly affecting the material's physical and chemical property. So as we see here, this is the small particle size, and it gives you, once we irradiate the sample with the light, and it gives you at a certain wavelength, and then after that it will emit certain rays. Yeah, for example, here it emits blue light, green light, yellow, orange, and red lights. Yeah. Okay, next one. Quantum tunneling effects. So in nano effects, we find a quantum tunneling effects. So which in nanomaterials occur when quantum particle like electron pass through a potential energy barrier that should be impossible according to classical physics due to their wave nature. But in nanoparticle, it can be happen. Yeah, this phenomenon significantly impact the electrical conductivity of materials at the nanometer scale, particularly in thin layer with nanometer dimension. Yeah. Quantum tunneling effects is as fundamental properties of nanometer scale electronic devices such as transistors, diodes, and altering their basic function because it can altering their basic functionalities. Yeah. And quantum tunneling effect has been successfully utilized to improve performance and energy efficiency in nanometer scale, like semiconductor devices, including tunneling transistor and tunneling random access memory. Yeah, or we know it as a RAM. That's the tunneling effect. And then next one is the surface effect. Okay, let me pause a bit my presentation because I will turn off my WhatsApp. I'm sorry. Okay, so then I will share my screen back. Okay, okay. Okay. This is the surface effect. As we know, the smaller the particle size, and we see the percentage of atom on the surface relative to the total atom proportional, it's become bigger. Yeah, as particle size decreases below 10 nanometer, the percentage of the surface atom increases significantly, reaching nearly 90% at 1 nanometer in this one. Yeah. And then smaller particle size have higher surface activity due to lower coordination and higher surface energy, yeah, making them unstable and reactive with surrounding gases. Therefore, now we know that there are so many improvements in gas sensing due to the development of nanoparticles, yeah. The surface area ratio increases drastically with decreasing particle size from 6.6 meters square per gram at 100 nanometer to become 660 meters square per gram at 1 nanometer. Yeah. Okay. High surface activity affect atomic transport, surface structure, spin conformation, and electron spectroscopy in nanoparticles, with carbon nanotubes being an extreme example consisting almost entire of surface atoms. Yeah. Okay. Now we go to the chapter 2 about the synthesis of nanomaterials. And maybe I think most of you already knows that the synthesis of nanomaterials consists of two methods. One is a top-down approach, and then the second one is bottom-up approach. We will see in this chapter about some example of them and how it works. Yeah. And first, we see the top-down methods. Top-down methods, which is bulk materials, are divided. So the ID, we divided to produce nanostructure methods. Yeah. The top-down approach, which is here illustrated in this figure, we have a big things, and then we try to dice them, and we get nanomaterials or nanoparticles. These methods, these things, top-down approach can be done by mechanical milling, etching, laser ablation, sputtering, and electroexplosion. Yeah. So this is the example of the ball milling, mechanical milling. So this is an example of one of the machine types. So here we have the ball bearing here, which is a small, and they will do, and then we will rotate the sample, including the ball milling. Therefore, the ball milling will dice our samples here that we want to achieve the nanomaterials or nanoparticles. Okay, the next one, electrospinning. So electrospinning is one of top-down approach where a high voltage is applied to a polymer solution. So as we see in this figure, there is a shearing which has a polymer solution inside. And then we applied a high voltage, and then it will produce a Tyler cone. Yeah, and it give a fiber jet, and we will get a nanofiber collecting in a collector, in our collector. Yeah. And then here, this is the example of lithography. Yeah, so here we have a silicon substrate, and then after that, we do a chemical etching here. And then after that, we can have a certain structure in our sample afterwards. Yeah. Lithography, it can be used light or laser or electron to dig the sample. And we have certain a certain pattern on our substrate afterwards. Or we can do a mask, or we can do via mass lithography, and we can get a nano pattern afterwards. Yeah. All right. Next one is a sputtering. So sputtering can be do as a top-down approach, since we have targets which is in bulk. Yeah. And then after that, through the plasma, yeah, and there is some gases or energetic ion will hit the target, and then after that, small particles will be condensed in our substrates. Yeah. And this is the arc discharge methods usually people use to make a carbon nanotube. It has a great significance in the generation of fullerene nanomaterials or carbon nanotubes. Yeah. So this is the source of gases that we use to make the carbon nanotubes. Yeah. Okay. Next one, the bottom up. Yeah. Bottom up approach involve assembling. So in top down, we have doing a dicing. Yeah. Cut the big particle into a small one, but in bottom up approach, we do assembling things. Yeah, we can do assembling of atom, we can do assembling of molecular or even another structure. Yeah. So a method that we can do for bottom up approach is supercritical synthesis. You can do spinning through spinning methods, sol gel process, and then laser pyrolysis, chemical vapor deposition, molecular condensation, chemical reduction, and green synthesis. Yeah. So this is at a molecular level, and then they are connecting each other, and it will become a nuclear and it grows. Yeah. So this is the example of the method which work best on bottom-up approach. This is chemical vapor deposition. So we have certain of gases, and then we mix them together, and they will create some sample that we want to make. For example, here we can have, for example, we can have carbon nanotubes can be do via chemical vapor deposition, or metal oxide films can be done via a chemical vapor deposition methods. Yeah. And then next is also plasma enhanced CVD. Yeah, this is this method CVD, PECVD. We have it in our research group. Yeah, or in our KK, we call it in Indonesia. So this is plasma enhanced chemical vapor depositions. It's also, we have a gas here. And then the gas is vibrate by a certain frequency power, and then it creates plasma, and then it gives us films in this substrate. Yeah. And then the PCVD application can be used as a solar cell, supercapacitor, and then also can be batteries, MOSFET, LEDs, and LED, membranes, sensors, and everything. Yeah. Okay, next one is solvothermal and hydrothermal methods. It's like, or you can apply, you put your solvent here, and then after that you heat it up and stir it up. Heat it up, maybe can be at 180 degrees and for certain hours. Hydrothermal, you can use we can use water for our solvent as a solvent, But solved for thermal, we can use another types of solvent except water, maybe like ethanol or DMF or anything. Yeah. So in hydrothermal methods, produce nanostructure material through a reaction in water at high pressure and temperature in a sealed vessel. The solvothermal method is similar but use a non-aqueous medium. Both methods are typically conducted in closed system in like a vessels, yeah, and high pressure. Of course, they will produce high pressure due to a high temperature. The next one, it's we can say it's like a simple or moderate way, because we can use just a reaction, precursor and solvent. They mix together and we can get aerogel or serogel and cryogel. Yeah. And then we do some mixing on it, and then we get some nanomaterials. Yeah. And this process including hydrolysis and then condensation and then aging and drying and then calcination. Calcination, you can use your oven or you can use microwave on it, or you can use calcination with with oven or vacuum oven, such like that, or you can use an oven with certain gases inside to improve the reaction of your precursor and solvents. Yeah. All right, next one is about the soft and hard templating methods. Yeah. This is, we have a template. Yeah, you can be a hard templates, like you have a hollow, yeah, like a molding, you can have a mold. And then after that, you can have a soft templates, can be from a polymer. And then you can have a colloidal templates. And then after that, we have a mold. The template can be mechanical molding, or we can be from polymers, yeah. And then we put fillings inside, anything that you want to make, and then after that we have a final structure. Maybe can be like a rod or a particle, or and so on. Yeah. All right, that's all the methods that we can use. Some methods, yeah, that we can use to create nanoparticles or nanomaterials, I mean. And next one is about the characterizations for nanomaterials. So we can discuss about introduction, particle size detection, detection and analysis of electrical properties, phase analysis and structure, detection of magnetic properties, how to do to study magnetic properties, how to do the thermal properties, how to do the optical properties, and how to do the mechanical properties. Yeah. So let's see here. So these are some example that we can devices that we can use to study about nano properties, nanomaterials properties. Like we have atomic force microscopy and Raman, X-ray fluorescence, deep profiler, oxygen nitrogen analyzer, cathodoluminescence particle analyzer, spectroscopy ellipsometry, photoluminescence, UV vis fluorescence, Raman spectroscopy. Maybe most of them you have known about it, and there are so many types of characterization that we can do. This picture just an example of them, yeah. So why is it important to perform material characterization? So the reason one is, first, the characterization reveal the detailed physical and chemical properties of nanomaterials. Yeah. And then the second one, properties change significantly. As we know before, maybe you already recognize from the energy level, because the energy level is different, so it will give you different magnetic properties, optic magnetic properties, and electrical properties also, yeah. So properties change significantly when the particle size is below 10 nanometers, enables manipulation and creation of new properties not present in bulk materials. And then the third one, essential for optimizing nanomaterials for various applications. And then the last one, crucial for advancing technology and science. That's why we need to do characterizations for the samples that we have made, yeah, from the previous sample methods that I have introduced to you. Okay, first about particle size detection analysis. The famous and the oldest method is optical microscope. Yeah, it's like optical, but with wide zoom here, or wide magnification. Yeah, so we can see in the level of micrometers. Yeah. And then after that, we can also see what's happening in our sample by times. So we know what's happening if we do some treatment to our sample. For these things, we need to, usually the optical microscope, it includes CCD camera. So you can do a real-time study about your samples. Yeah. Okay. Next one is scanning electron microscope. So maybe most of you already get used with this microscope. So in SAM, or we call it SAM, we can do a detection to our sample in the surface morphology. And SAM also can be studied about the composition and structure of a wide range of materials. Yeah, this is how it works. For the sample, we have electron gun, as it knows, scanning electrons. So it has electron gun, and then it focus to your sample and irradiate your sample. And then you will have a detector, because from this electron gun, they will give you a backscattered electron and secondary electron. And we will detect it through our detector and image. And there will be do imaging to our sample. This is an example of nanoparticles, which has something like a size of this is maybe in 10, maybe this is bigger, and this is in range of hundreds of nanometers. Yeah, this one. Okay, the next one, this is the high resolution, which has we call it transmission electron microscope, which is TEM. We call it TEM. So TEM, it can be more detailed for your analysis, picture analysis here, because TEM is an indispensable tool in many scientific and industrial fields, providing unparalleled insight into the internal surface. So you can see even in what is inside of your particles and composition of the material in atomic level. Yeah. So from TEM, we can study about atomic scale in atomic scale level, because it gives you a better resolution from the previous characterization. Yeah. Now, this is more advanced for this thing. So you have advanced rules, like you have to go to a simple one, which call it single or wide angle X-ray scatterings. Yeah. So maybe this is new from you. Yeah. Single angle X-ray scattering, or wide angle X-ray scattering. So this is due to a scattering effect that we have. We have an X-ray source here, and we focus, and then this is our sample, and then it's will scatter the rays, and then after that it can be projected in particular in very small and details. Yeah. So SAX and WAX is powerful tool for comprehensive study for structural and conformational features for macromolecules at a size ranging from angstrom to hundreds of nanometers. Yeah. So you can see about the bacteria here, virus, or you can see a quantum dots even. You can see from, or you can see about the interaction between electrode in your sample. You can use this characterization. So SAX, TEM, and SAM are complementary techniques that provide different types of information about materials. SAX is ideal for studying the overall structure and distribution of nanostructure in a non-destructive manners. SAM excel the providing details about surface image, and TEM offers unparalleled resolution for examining internal structure at atomic level. Yeah. So if you want to be, so first you can go with your optical microscope. Oh, my sample is already so small. Okay, you can go for SAM to have a surface image. And then if you want to do more detail in atomic level, you go with TEM. And if you want to see overall structure of your particles, you can see it in X-ray scatterings. Yeah. All right, so next one is electrical properties. So for study the electrical properties, you can get information about the conductivity, yeah, conductivity, resistivity, carrier mobility, how quickly charge carriers can move through a material when an electrical field is applied, and then the electric properties and Seebeck coefficient. Seebeck coefficient, you usually use it while you study about transistor, yeah, a measure of the thermoelectric effect indicating how a material converts temperatures differences into electric voltage. So how to do that? First method that you can do is like a 4-point probe, yeah. 4-point probe arranged in an equally spaced linear configuration probe. So you have 4 probes here, and then you can apply to your samples, yeah. And then 2 of them has you can give a voltage, and then the outer one will be given as a current, yeah. And then it will result a voltage drop across the 2 inner electrodes. This setup is used to measure the resistance of a material, which in turn can provide information about the material's conductivity. Yeah. And then the next method that you can use to study the electrical properties of your sample is via electrochemical impedance spectroscopy. Or we can call it, it's EIS, yeah. EIS is, or in Indonesia, we know it's AES, we call it AES, yeah. It's a powerful technique that applies an alternating currents to a sample and measure the resulting impedance to the analyze its electrical properties such as resistance, capacitance, conductivity over a range of frequency. Yeah, usually people use it if you study about battery, supercapacitor, you want to study about what's happening in the surface of your sample, yeah. Okay, this is an example of the measurement. Okay, next one. Next one is field effect transistor measurement. So this is how you study to characterize your sample. If you make a transistor, use a semiconductor device with a gate, source, and drain to measure the current voltage characteristics and determine their mobility. Yeah. So usually commonly used to evaluate the electrical properties of nanomaterial like carbon nanotube, graphene or nanowire in transistor configuration. Okay, continue. Okay, next one is a scanning probe microscopy. So, or SPM, yeah. SPM also include with STM, so you can study about the tunneling currents on your sample. Measure tunneling current to provide atomic scale image and information on electronic states, because SEX, you can use it for a study about the whole structural process, but it's very expensive. You need synchrotron from that, and an alternative of that, you can use STM, yeah. And then you can also study conductive atomic force microscopy. It's happening, it's busy. Measure for conductive atomic force microscopy, or AFM, it's like you have a cantilever here, and then through, for example, for STM, for tunneling current, it can be imaging your sample. But for AFM, it's you have a cantilever and you scan it. It's like we tried. Oh, I think, I don't know, you meet it while in what I was in school, in elementary school, we have a mapping picture. To map a picture, we do like a cantilever moving around our figures, something like that. This is the same what's like for AFM, yeah, AFM. Okay, next one, dielectric spectroscopy. So this is the principle of these measurements is the dielectric response of a material to an applied currents, electric field over a range of frequency. The application of measurement usually used to study the electric properties, polarization mechanism, and relaxation phenomena in nanomaterials. Yeah. Okay. Next one. This is about how we study the structure of our materials. How to move this panel? Okay. So for phase analysis, structural properties, we can do some characterization. We call it structural properties, which from this study, we can analyze the crystallinity of our sample, phase composition, grain size, defect, and atomic arrangements of our sample. And how to do that? These are some characterization. First, X-ray diffraction. I think everyone already knows about X-ray diffraction, yeah? So we can know about the structure of our sample, whether it is in crystal or it's in polycrystal or in amorph structure. And we can see the diffraction patterns and also the Brillouin structure of our sample, yeah? Next one, X-ray fluorescence. X-ray fluorescence, the most suitable and widely used technique for determining the chemical composition of powder-based nanomaterials, yeah? This method is versatile, enables the spectrochemical analysis of nearly all elements, yeah? So if you want to know what do you have in your sample, whether you have a carbon, nitrogen, or iron, or everything, for example, usually people from earth physics and also nuclear physics, for example, if you want to know what is you have in your soil, if you go to, for example, to certain area, and then this area have nuclear, or they have active volcano, and you want to see whether what minerals in your soil, something like that, you can do with X-ray fluorescence, yeah, to study or what is the contents. Maybe you have a gold there, or maybe you have noble minerals in your soil, yeah. So maybe from maybe most of you guys comes from a different city in Indonesia or maybe abroad. So maybe you can study what is in what minerals. So you can use this kind of characterization. Yeah. And also we can use for structural properties, we can do via Fourier transfer infrared spectroscopy, or we call it FTIR. So the principle is measure the absorption of integrated light by the material to identify chemical bonds and molecular structure. Yeah, so we can see we will have a spectrum like this, and we see the bonds relates what kind of bonds that we have in our sample. The application of this characterization is useful for to chemical composition study the bonding environments within the materials. Yeah. Okay, next one, Raman spectroscopy. In principle, Raman quite similar with FTIR, but in Raman require minimal sample preparation, and it can handle aqueous samples, yeah, or liquid samples, and allow non-destructive analysis through transparent containers. It provides higher spatial resolution, detect low frequency vibration, and minimize fluorescence interferences, making it more versatile for various sample types. So you can have a fingerprints of your samples. Yeah, you can see it because it can detect in low frequency. Okay, so you can see the Raman scattering also here, yeah? Okay, next one is magnetic properties. In magnetic properties, you can study about the magnetizations, which is magnetization is the degree to which materials become magnetized in response to an applied magnetic field. And then you can study about magnetic susceptibility, which is measured the extent to which materials becomes magnetized in an external magnetic field. And then you can study about the magnetic coercivity, yeah, the resistance of magnetic material to change in its magnetization, and measure to the material's magnetic hardness. And then magnetic saturations, the maximum magnetization a material can achieve under an applied magnetic field. And then this for information you can get via hysteresis loop. Yeah, a plot of magnetization versus applied field, magnetic field, showing the relation between the 2 and the 3 loss due to the hysteresis. How to do that? You can do via vibrating sample magnetometer or VSM. So this is your sample. You have electromagnet here, and then the sample will be vibrate, and then you can get the hysteresis loop afterwards. Yeah, they measure the magnetic moment of a sample by vibrating it in a uniform magnetic field. The induced voltage in surrounding pickup coils is proportional to the magnetic moment. Yeah, so here you can get information about the magnetization, coercivity, and saturation of bulk materials, powders, or even thin films. As you see here, this is our hysteresis loop. And here we can define whether we have a super paramagnetic. Our loop will be like the blue color. And then if we have a ferromagnetic, it will be like the red color, yeah. Okay, so we can get information, the paramagnetic and diamagnetic information we can get from our sample. Okay, this is the coercivity. So if you want to know the coercivity value, you can read this area, and then if you want to know about the magnetic saturation, magnetization, you can read this part. Yeah. Okay. Next one is magnetic force microscopy. So in principle, it's the same like AFM, but in this case, you have a tip which has magnet inside, so they can make a mapping of the magnetic area of your sample. Yeah. So it will do a scanning through your sample, and it will be project the magnetic mapping of your sample. Next one, this one is the advanced characterization because it is superconducting quantum interface magnetometer. So it has a conductor coil, yeah, and then your sample will put in straw, and then it will move up and down through this coil, yeah. This is very sensitive magnetometer used to measure extremely weak magnetic fields. And based on superconducting loops containing Josephson junction, squid are sensitive and it can detect a magnetic fields as low as 5 × 10⁻14 Tesla. Yeah, as long as your sample is magnetic, yeah, a good magnet. If your sample is not a good magnetic properties, it will you cannot detect with the squids. And this squid also can study about a living organism. What is the signal? Because our body works based on a magnetic. Yeah, that's why in our blood has content of iron, and that iron has have a good magnetic, ferromagnetic, so we can study about our organism, whether it works properly or not. Yeah. All right. Next one. Next one is nuclear magnetic resonance. So, or we call it NMR. NMR spectroscopy exploits the magnetic properties of certain atomic nuclei. When placed in a strong external magnetic field, this nuclei can absorb and re-emit the electromagnetic radiation at specific frequency. The key to NMR is the nuclear spin, a quantum property that certain isotope possess. Yeah, you can study about spin states of your sample via NMR, or you can DNA. It's also can be studied through NMR. Okay, next one is thermal properties. In thermal properties, you can study about the thermal conductivity, specific heat capacity, and then thermal expansion, and then thermal stability. Yeah. Thermal conductivity measures the ability of material to conduct heat. High thermal conductivity materials efficiently transfer heat, while low thermal conductivity materials act as a thermal insulator. So this characterization, you need it while you study about the thermal transfer materials. Yeah. Specific heat capacity indicates the amounts of heat required to rise the temperature of a unit mass of the material by 1 degree Celsius. It reflects the material's ability to store the thermal energy. And then thermal expansion describe how the size of a material changes with temperatures. Material expand when heated and contract when cooled. Yeah, usually you combine this characterization, their mechanical properties. Yeah. And the next one, thermal stability, refers to the material's ability to maintain its structural and chemical properties at high temperature. Okay, next, let's see how to do that. To study about the thermal properties, you can use differential scanning calorimetries, or you know it, or people call it DSC, yeah, or in Indonesia, DSC. You put gas, you put your sample, there is a gas inlet on it, and then you heat up your sample. So the principle of this characterization measure the heat flow associated with the phase transition. So you can see the phase transition of your sample start, such as when it melts, when it's forming a crystallization or other things. Or you can learn how the reaction happen in your sample through this characterization. Yeah. And then the application use of this DSC characterization used to determine specific heat capacity, glass transformation temperature, and thermal stability of nanomaterials. Usually, the DST characterization combined with TGA characterization, which is thermography metric analysis. Yeah. So in this characterization, you can learn about the thermal stability, the composition, and moisture content of your sample. So the principle, this characterization measure change in the weight of your sample. So you burn your sample. It means not you applied certain temperatures, so until it get burned. And then providing information on the thermal stability of the composition of your sample. Yeah, the application of this characterization used to assess thermal degradation, composition, and stability of nanomaterials under controlled heating condition. Yeah, all right. Next one, optical properties. So to start the optical properties, you will get information about the absorption, the reflection, the transmission, scattering, and luminescence of your sample. So absorption, the process by which a material absorbs light and convert it into other forms of energy. Typically, it's like a heat, for example. The absorption spectrum provides information about the material's electronic and optical transition. Reflection, the reflection of light that bounces off the surface of a material. Reflectance measurements can provide insight into surface properties and coating effectiveness. Yeah. And then next one, transmission. The fraction of light that passes through a materials. Transmission spectra reveal information about the material's optic thickness and transparency of your samples. Yeah. And then next one, scattering. Scattering, the redirection of light by particles within the materials. Scattering study can provide information about particle size, shape, and distribution. Yeah. And then luminescence, it's like emission of light by a material when it absorbs photons. This includes photoluminescence and electroluminescence of your samples. So how to do that? Okay, this is how it works. Optical measurement effectively reveal materials property related to light interaction. So the light can be infrared, UV, it can be any kind of light, yeah. And then, but it depends what you want to learn, yeah, because light has a any kind. The light will have energy, and the energy that emit from the light, they have a certain wavelength. So it depends what you want to approach in your samples. For example, a UV-vis or UV visible spectroscopy. So here you use a UV light, yeah. And then this is the light source, and then dispersive element, and then this is your sample, and then you can have the spectrum of your sample. Yeah, the interaction of your sample while we give the UV light. Okay, the principle, the measurement, the measure the absorption or transmission of ultraviolet and visible light by materials. The resulting spectrum provide information on electronic transition and band gaps, because UV has you approach something like between 260 nanometer, which is equal to the band gap of semiconductor. Yeah, that's why you can learn about the band gap and electronic transition of your sample. An application of this characterization used to determine absorption spectra, band gap, and electronic property of nanomaterials like quantum dots and nanoparticles. Yeah. All right. This is a different size emit different lights. Okay, now photoluminescence spectroscopy. So here you use laser in certain wavelengths, for example, 365 or 342, yeah. And then the principle measure the emission of light from a material after it has been excited by a light source. So it's depend which wavelength do you want to use, yeah. The emission spectrum provide information about electronic and optical properties. This characterization useful for studying the luminescent properties of quantum dots, nanorods, and other luminescence nanomaterials. Next one is fluorescence spectroscopy. So in fluorescence spectroscopy, it's quite similar with photoluminescence spectroscopy, but focuses on detecting fluorescence emitted from a sample when it is exciting by a specific wavelength, yeah, or of light. The application often used in biological imaging and sensing application to study fluorescent nanomaterial and their interaction with biological systems. And then the last one is SPR, surface plasmon resonance, which the principal measure change in the resonant condition of surface plasmon wave as a function of refractive index near the surface of materials. The application used to study interaction at surfaces such as binding events and change in optical properties of metal nanoparticles. Next one is mechanical properties. In mechanical properties, you can get information about the hardness of your sample, elasticity of your sample, tensile strength, fracture toughness, Young's modulus. Yeah, how to do that? You can use comprehensive and tensile testing. Yeah. So for example, this is before and after you do a tensile and compress your sample. Yeah. Okay, and this is dynamic mechanical analysis, DMA. So this is your sample. You've applied a force to your sample, and you also applied a temperature. The principle measures the mechanical response of a material under oscillatory stress, providing data on elasticity, viscosity, and viscoelectric behavior. The application used to study the mechanical property of polymers, composite, and other materials over a range of temperatures and frequencies. Next one, ball-on-disc tribometry. So there is a ball here, which is this is a disc which can be rotated, and then it measures the friction and wear by pressing a ball against a rotating disc and recording the focus involved. The application of this measurement can be due for evaluate tribological properties and wear resistance of nanomaterials. Yeah. Okay, that's all about the characterization. Now we continue to chapter 4 about carbon-based nanomaterials, which is include about introduction, characteristic of carbon-based nanomaterial, graphene and its derivative, carbon nanotube, nanodiamond, fullerenes, and carbon nanodots. So let's see here. So these are a family of carbons. So here graphene quantum dots, fullerene, carbon nanotube, carbon nanoanions, nanodiamonds, and we can find it, we can applicate it in tissue and engineering, drug delivery, and then photothermal therapy, gene delivery. Yeah. Okay, let's have a look. These are the characteristic of carbon-based nanomaterials. Yeah, they have extraordinary mechanical strength, high electrical and thermal conductivity, and unique optical properties. Yeah, they also have a high surface area, the ability to chemically functionalize, and then as we see here, this is zero dimension of carbon, like nanodiamond, graphene quantum dot, carbon dots, and then fullerenes. And then for one dimension, multi-wall carbon nanotube, single wall, and quad nano fullerene. And then here, the two dimension can be graphene, RGO, GO, graphene, and C3 and 4. Yeah. Next one, it's about graphene and its derivatives. So this is the carbon atoms. They have like a hexagonal structure. Yeah. The distance between two atoms is 0 0.42, 142 nanometers. It has molecular bonds. Yeah. That's why they can be modified or doped by other atoms because they only have a molecular bonds, van der Waals bonds. So graphene, one of the thinnest known material, boasts excellent mechanical strength and transparency, making it ideal for transparent light panels and touch screen. Yeah. Additionally, it has an exceptional high theoretical surface area, significantly suppressing that of fullerenes and graphite. Yeah. This is graphene's application derivative. Yeah. Graphene can be application as a lithium sulfur battery, can be applied for supercapacitor, sodium ion battery, lithium battery, and lithium ion battery. Yeah. So they have a lot of advantage of each of them. Yeah. Next one, this is a comparison of the properties of graphene, graphene oxide, and reduced graphene oxide. So this is a pure graphene. This is your graphene oxide, which has oxygen. And this is reduced graphene oxide. The oxygen here is reduced by certain method, and you still have a small amount of oxygen on your graphene. Yeah. So pristine graphene is a single layer of two-dimensional carbon atoms, consists of carbon atoms and no oxygen. It has sp2 hybridization, no defect-free. And the preparation of the sample is a bit tricky, and the production cost is high, and also can be do a simple way by a Scott tip. Yeah. And then electrical conductivity is high for pristine graphene. Graphene oxide, heavily oxidized graphene consists of carbon, oxygen, and hydrogen, And then it has sp2 and sp3 hybridization. It has a direct, and the preparation is quite easy, and then the production cost is low, and the electrical conductivity is poor. Reduced graphene oxide, a reduction from graphene oxide, which still have carbon, oxygen, and hydrogen, depends upon the synthesis process. So the more direct process, the less oxygen you will have it. Predominantly, you have sp2 hybridization, but you still have slightly sp3 hybridization. Defects still present, but quite a small amount, and easy process, low production cost, and the electrical is depend how much oxygen that you still have in your sample. Yeah. The smaller oxygen bonding you have in your sample, the better conductivity will you get for your sample. Okay, and then this is a graphene oxide and reduced graphene oxide, the application in biomedical. So it can be, you can use it as tissue engineering, you can do a drug delivery, phototherapy, and then bioimaging. And then this is graphene oxide and folic acid nanocarrier. You can use it for drug delivery and also for screening for tumors. Yeah. Jadi you have a drug and then it release and then it can kill your cancer tumor, your cancer tumor. And then next one is carbon nanotube. As you see here, the single one, double wall and multi-wall carbon nanotubes. And how do you make it carbon nanotube? It can be zigzag, armchair, and chiral. It depends how you do this, yeah? How you roll it. And this is some properties of carbon nanotubes and the application of carbon nanotubes. So here, the property of carbon nanotube, it has selective enrichment of the molecule, and then construction, and then they have construction of heterostructures, and then more modularization of energy bands. We can applicate due to material synthesis, large devices, and device manufacturing, and smaller devices too. And nano diamonds. So this is a nano diamonds, a small of carbon structure. And then nano diamonds can be application for many things. Nano sensing, catalyst. You can use it for separation, nano separation. And then nano cosmetics, gene delivery, and drug delivery. Yeah. Okay, and then we have a fluorine, which is C60 here. So if you have 60 carbon, they will form a ball, which we call it C60. And we can dope. The doping can be inside the cage or outside the cage. So in between 4 of the fluorine, and they will have magnificent properties like supermagnetic properties if you can isolate one atom of sodium inside of the cage. Yeah. This is application of fluorines and carbon dots. Carbon dots, we just get a Nobel Prize previously. So it has high quantum yields. It has a good biocompatibility, eco-friendly, good stability, electron transfer, strong absorption. It can be application as an optoelectronic biomedicine sensor, anti-counterfeiting, catalysis, energy storage. Yeah. So carbon dots, a new type of carbon-based nanomaterial, have attracted board research interest for years because of their diverse physicochemical properties and favorable attributes like good biocompatibility, unique optical property, low cost, eco-friendliness, abundant functional groups, and high stability and electromobility. Yeah. This is a family of carbon dots. Carbon dots can be graphene quantum dots, yeah, which is like a graphene, but it's in a very small size, yeah, in dot size. And then you also can have carbon quantum dots, yeah, and then also carbon polymer dots, which is like this one. It has carbon dots, this green one, and it has a polymer inside. And then, okay, it can be, oh yeah, these carbon dots can be generated from biomass, polymer, or small molecule, or cutting from graphene, graphite, or fullerenes, yeah? Okay, how to approach it? Okay, I think I will make a break while Azan comes close to my house because my house close to a mosque here. So here the synthesis process of carbon dots, yeah, it like what Liu do it can make a certain luminescence from the carbon dots like blue, green, and red emission. Okay, next one. This is also application of carbon dots, yeah, in rechargeable battery. And then this is for biological. You can use as for bioimaging, yeah. You can inject the carbon dots inside an animal, yeah, rats, and then you can do imaging on it. And then biomedical application, like for cancer, to destroy a cancer, and also for drug delivery. It can also be done by carbon dots. Yeah. Okay. Now we go to the last chapter about exploring beyond nanomaterial. I think I will pause for a while because there is an azan here. Yeah. Maybe we will pause for 3 minutes. Is it okay, Arum?
Yes, is it okay?
Okay, thank you.
If you have any question, you can write down your question in text box, in chat box, while waiting the lecture.
Okay, let's continue. So chapter 5, exploring beyond nanomaterials. So this is I pick 3 of our research, and we will discuss about it here. So about graphene quantum dots, or recently we call it as carbon dots. And then reduced graphene oxide for transparent conducting film. And then 3D polymeric materials, or we call it hydrogels. Yeah, okay, let's have a look on it. So graphene quantum dots, as we discussed before, it have received enormous attention because of their unique chemical, electric, and optical properties. So various approaches developed to prepare graphene quantum dots include acidic oxidation and hydrothermal synthesis, microwave synthesis, electrochemical synthesis, oxygen plasma, and so on. Yeah, in this work we do via hydrothermal synthesis. So as you see here, this is graphite, carbon fiber, carbon nanotube, graphene-based materials. And from top down, based on top down methods, we can get carbon dot from graphite. We can get graphene quantum dot, carbon fibers also, carbon nanotube, we can get carbon dots on it. Same with bottom up method from citric acid, glucose, glutamic acid, fullerenes as a precursor, and then we can get graphene quantum dot afterwards. Yeah. Okay, and then Tang et al. First reported a simple method for preparation of graphene quantum dot by microwave assisted hydrothermal. So after they do hydrothermal, they do microwave method to reduce the oxygen and to create the dots on it. The formation step of the graphene dots were depletion and surface growth, followed by development of self-passivation layer. And then Dong et al. Reported a pyrolysis method to selectively prepare graphene quantum dots and graphene oxide by controlling the carbonization of citric acid. And then Q et al. Investigated the effect of atom doping on graphene quantum dots, sodium dot, or nitrogen dot using the hydrothermal method. From his research, he see that the greatest PL performance was achieved with graphene quantum dots that were synthesizing from citric acid and urea as precursor. We also do the same things. We use citric acid and urea, but we use a hydrothermal method, and we see what's happening in our sample with the characterization from time XPS. XPS is X-ray photoluminescence spectroscopy. You can define the bond structure and also chemical composition in your sample. We also study about the UV phase and energy electron loss spectroscopy to study about the structure of our sample. Yeah. So here in this report, we report about the rule of interaction or bonding between carbon and nitrogen, and the configuration and relationship between them. As we see, there are 3 types bonding exist in the graphene quantum dots, which is graphitic, which is nitrogen and carbon bonding here. And here pyrolytic, also carbon and nitrogen bonding, but it's in the edge of the dots. And there is a carbon and a nitrogen bonding, but it has 2 bonds on it. So here from the illustration of the PL mechanism in quantum dots, so you have a certain interaction on it, excitation and recombination happens in the structure. And here about the PL intensity, so we varied the times, the hydrothermal times between 50, 90, and 180, and we study about the distribution of these 3 bonds on the sample. And this is the time image of the sample and also the AFM image of the sample. This one, and the profile of the sample. Yeah, you can see here there is the dots of the quantum dots. Also here from the time image. Here they are, the distribution of the bonding between pyridinic and graphitic in your sample based on the hydrothermal times. Yeah. So we do in 50 minutes, 90 minutes, and 180 minutes. Sorry, I mean here in minutes, yeah. So it's quite fast, yeah. Okay. And then this is the optical configuration. You see the contribution of carbon, nitrogen, and oxygen here. And also from EELS spectrums exhibit main peaks in 295 and also 401 EV and 534, which are attributed to the key edge C of C, nitrogen, and oxygen respectively. So it's indication of the carbon, nitrogen, and oxygen on our sample based on EELS spectrum. And then the key finding of our research is the emission mechanism of the graphene quantum dots depends on sp2 cluster that are isolated between the sp3 CO matrix, carbon oxygen matrix. Yeah. The CN configuration, which is pyridinic, pyrrolic, and graphitic, contribute 1 or 2 electrons respectively to phi at graphene quantum dot sp2 as the localized electrons. So there is a localization of electron there. And then the localized electron is excited to phi star bonds at sp2 carbon with the phi electron of the sp2 carbon bonding. Yeah. And then the presence of pyrrolic N as a pentagonal structure in graphene quantum dot leads to non-radiative transition of the excited electron. And then the excited electrons recombine with holes in the phi bonds at graphene quantum dot sp2. PL is emitted from the sample at an emission wavelength of approximately 460 nanometers. So next one is about transparent conducting film from reduced graphene oxide. As we know that graphene has remarkable properties like flexible, very strong, high electrical conductivity, transparent, high thermal conductivity, high surface. Therefore, it is promising to be can be application as a transparent conducting films, which can be used in solar cell, touchscreen, smart window, flexible OLED. Yeah. And this application depends on the resistance that we have in our TCF. For example, for touchscreen, you need 500 ohm per square. And for solar cell, you need a resistance of 1 ohm per square meter for square. Okay, next one. Usually, people use ITO and FTO, which is expensive, unstable, and high cost fabrication. And there is a lot of defects on it, and also it's toxic. Yeah. Therefore, we need to find a more friendly green materials, which is graphenes. Yeah. Okay. So here we fabricate transparent conducting films. It's free from metal oxides, and then which is metal materials. It's raw material on Earth. Raw material on Earth is scarcity, and then it has excellent properties. Yeah, this is the result that we have. This is our films. It's homogeneous films on it, and it has a thickness of 95 nanometers. and it has carbon peak based on express structure carbon, nitrogen on oxygen peak on it. And then we can see about the carbon structure that we have a lot of carbon bonding on it. And we here we do the reduction of oxygen via microwave, and and from this spectrum we see the reduction of oxygen on our sample. So therefore we use X-ray photoemission spectroscopy to study the content of oxygen in our sample. And then this is the conductivity of our sample. So it has the conductivity becomes small after we introduce in microwave or if we heat it, and the transparent is quite good, it's 30%. Okay, the key findings of this research, we have environmentally friendly reduction. Graphene oxide film were fabricated using L-ascorbic acid as a non-toxic reduction agent with thermal reduction assisted by microwave irradiation. And then we have even film deposition. The geofilms were deposited evenly on the substrate using drop testing method. You just drop the sample on your sample and then you do some treatment, heat treatment on it, providing a simple and effective alternative to spin coating. And that it has good properties. So it has with microwave irradiation improve the property of the films IDIG 74 to 1.2, and the resistance is also decreased from 3,000 to 4 kilo ohm per square. Yeah. Okay, the microwave procedure method also increase the carbon-carbon bonding and reduce the carbon-oxygen bonding. Yeah. And then improve electrical and optical characteristics. The study investigated and demonstrated enhanced electrical and optical properties of the RGO film, emphasizing effectiveness of combining chemical and thermal treatment for the reduction process. Okay, the third one is hydrogel. Hydrogel is a three-dimensional polymer material capable of absorbing a lot of water due to the presence of hydrophilic functional groups on it. So hydrogel polymer, there are two types of polymers, synthetic and natural polymers. Synthetic polymer has excellent mechanical properties, easy to form, high reproducibility, but the weakness is high production cost and the possibility of containing toxic substances. Natural polymer have a strong property, which is easy chemical modification, cheap, and does not contain toxic substances. Biocompatible and biodegradable, but it has a poor mechanical properties. So here we do a cross-link play and cross-link. This cross-link play an important role in the structural development of hydrogel. A cross-link is defined as a bond that connects two polymer chains, yeah, to form a stable structure. Okay, next one, the crucial property of a hydrogel. It can be the morphology, porosity, swelling ability, mechanical properties, thermal properties, and biocompatibility. So here, if you make a natural polymer, so in this case, we make a natural polymer, and we need to study these properties in order to prove that we have a good properties of our polymers. So here we make a polymer from glucomannan-based hydrogel. So these are the properties. And then this hydrogel, it has a high strength hydrogel, so it's natural material, and then it can be used for tissue engineering, wearable sensor. It can be used for battery also, contact lens, actuators, and wound dressing. Yeah. Here we use glucomannan based hydrogel, which can be prebiotic effect. We have study about the prebiotic effect, which is good for our body. And then it has a good antibiotic agent, antioxidant agent, and antibacterial agent. That's what we found from our glucomannan-based polymer that we have. And then this hydrogel can be high flexibility, and mechanical properties, thereby reducing device retention, signal detector, so we can swell it because it's biodegradable, and we can because it's as edible, we can use it as edible electronic also, because it's compatible for our body. Yeah. Yeah, this is nice. Yeah, see, and then prebiotic effect. So from biodegradable material, it has a prebiotic effect, anti-obesity. So you don't, it doesn't contain a lot of glucose. And then antibacterial activity, good active antibacterial, antioxidant also. Edible electronic provide devices that are both electronically functional and safe to consume. They can be utilized for sensing, tracking, and monitoring for diagnosis, treatment, and therapy of human body. Yeah. And then this is the hydrogel. The nature of hydrogel in general is intriguing to the ability to integrate with other materials. So we can combine with also natural, for example, turmeric, or we can also combine with another health material, which is good for our body. Yeah, we can use it as a drug also. Okay, the last one, the future direction, challenge, and ethical consideration. So future directions, enhance functionalization. So advancement, developing new methods for functionalizing nanomaterial to improve their performance in various applications. Yeah, such as targeted drug delivery and advanced electronics. The goal is to enable precise control over material property and enhance their utility across multiple fields. The second one, sustainable production, advancement, developing greener and more sustainable methods. Therefore, we can reduce waste and energy consumption. The goal is to minimize the environmental impact and make the production process more eco-friendly. And then the third one, biomedical application, advancement, expanding the use of nanomaterials in medicine for diagnostics, therapeutics, and regenerative medicines, edible electronics. And the goal is to improve early detection of disease, targeted treatment, and tissue engineering techniques. Yeah. Maybe tissue organism. We need it someday. Yeah. Okay, and then advanced electronics. Advancements utilizing nanomaterials to create more efficient, faster, and small, because everything we need electronics nowadays, we cannot far away from electronics, right? So the goal is to push the boundaries of electronic performance and integration in the next generation technology. And then the fifth one is, wait a minute. I need to answer. Environmental remediations. So employing nanomaterial to clean up pollutants and contaminants in soil, water, and air. The goal is to develop efficient and effective methods for environmental protection and restoration. And then for energy storage and conversion, innovating nanomaterials for battery energy storage solutions such as high-capacity batteries, supercapacitor, and improved energy conversion technology. The goal is to enhance the efficiency and longevity of energy storage system and renewable energy source. Now, the challenge, I think all of us which is here are the students in material research, right? So the challenge for us for doing this research is the scalability, characterization and standardization, and safety and toxicity. So for scalability, the issue is scaling up the production of nanomaterial from laboratory to industrial. The solution develop cost-effective and reproducible manufacturing processes. Characterization and standard. The issue is a lack of standardized method for characterizing nanomaterials, which may lead to inconsistent results. Solution: establishing universal standard and protocols for characterization and testing. I hope that after our lecture, you can get a sense if you want to do a characterization for your synthesized materials. Yeah. And then safety and toxicity issue, potential health and environmental risks associated with the use of nanomaterials, including toxicity and long-term effects. Yeah. And the solution, conducting comprehensive safety assessment and developing guidelines to mitigate the risk. And then next one, regulation and policy, developing appropriate regulation and policies to govern the use of nanomaterials and ensure safe practices. Solution, formulating clear and effective regulatory frameworks that balance innovation with safety. And then the next one, cost and economic viability, high costs associated with the production and application of nanomaterials, reducing costs through an advancement in manufacturing technique and economies of scale. And then next one, integration with existing technology. Integrating nanomaterial with current technology and system can be challenging. Solution, fostering interdisciplinary research to facilitate seamless integration and compatibility. Ethical consideration that we need to consider: health implication and environmental impact, equity, and accessibility. For health implication, the concern is potential unknown long-term health effect of exposure to nanomaterials because it's very small. Yeah, okay. And then ethical approach, ensuring through testing and transparent communication of risk to protect public health. Environmental impact concern the potential for nanomaterial to cause environmental harm if not properly managed. Yeah, therefore we need to implement sustainable practices and conducting environmental impact assessment. And then next one is equity and accessibility, ensuring that the benefits of nanotechnology are accessible to all and not just a privileged few. Ethical approach, promoting equitable access to nanotechnology and advancement and addressing disparities. Yeah. Privacy, they concern the use of nanomaterials in surveillance and data collection may raise privacy issue. Ethical approach, developing privacy safeguards and regulation to protect individuals' rights. And then the next one, informed consent. Our concern is ensuring that individuals are fully informed about the use of nanomaterials in consumer product or medical treatment. Ethical approach, providing clear and comprehensive information to consumer and patient. And then public perception. The concern is addressing public concern and misconception about nanotechnology. Ethical approach, engaging in open dialogue and education to build trust and understanding. All right, that's all my presentation. I would like to say thank you for you all. It's almost 2 hours, yeah, I talk in this lecture. And I would like to special thanks to my collaboration, Professor Khairul Rijal, Professor Ferry, Iskandar, Professor Nikra, Judith, Dr. Ari Bowo, Dr. Roni Sutarto and Dr. Fitri Aulia, Permatasari for the collaboration. And also to all my students, candidate Dr. William, who also helped me to make these slides, Dr. Octaviardi, Rahmat Hidayat, Dina Rahmawati, Salma, Arida, Naila Rizki. There are also some of their work also present in this slide. Okay, that's the end of my presentation. I hope it's good for you and you get useful information from this lecture. Thank you very much, and I will let Arun lead this session. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you very much to Dr. Akfiny for your interesting lecture. This is any question from Jonathan Sugianto from ITB. Let me read. First of all, thank you for insightful presentation about nanomaterial. In your talk, you have mentioned some example of nanomaterial from 0 dimension to 2 dimension. However, most or perhaps all of them are carbon-based. Why is there a particular reason why carbon dominates the nanomaterial industry? And the second question, are there other potential alternatives to carbon for some types of nanomaterials? I'm particularly interested in application which requires good magnetical properties, since as far as I know, carbon is non-magnetic. Dr. Akfiny, can you answer this question?
Good question. Good question, Jonathan. So, about your questions, maybe you see in my presentation, most of them I talk about carbons. Actually, why I delivered about carbon, because carbon is less toxic materials, yeah, because it is organic material and less toxic. And then, of course, it can be some minus of this material because it doesn't has very good magnetic properties, for example. The reasons why carbon dominates in nanomaterial industry, because is it easy to find. So is it organic material? So easy to find. You can get carbon from leaf, from wood, from flower, from anything that you have around you in this earth. And then that's why carbon can be dominate. But it's also have some properties like magnetic properties, not really good as inorganic materials. Before, people focused in research doing inorganic materials like cadmium sulfide. This is the first material that people found about quantum dots effect. But after all, people find in carbon, they also find a quantum dots effects, like in carbon dots or graphite quantum dots, for example, like that. And then the second, I hope the first question is answering you. Because in carbon is organic, less toxic, easy to maintain, easy to produce, and they have a diverse application. Indeed, the lifetime of material is also questioning, yeah. And then the second question, are there other potential alternative to carbon for some type of nanomaterials? I'm particularly interested in application which require good magnetical properties, since as far as I know, carbon is not non-magnetic. Yes, That's the point. What I told you, that's the minus point of a carbon material. It doesn't have a good magnetic because it doesn't have the spin we cannot control on it. For this case, it is better to use because carbon is a D6 materials. So the electron already full. So we cannot play on the spin or electron structure. It will be different if we have iron to overcome this problem. Usually people dope graphene with iron or with nickel or another inorganic material. So carbon cannot stand alone to provide all the application. No, because they also need inorganic material like iron, as I said, cobalt, nitrogen, and so on to advance their properties. I hope it answers you.
Okay, Jonathan, maybe this is answer your question. Is it clear? Okay, thank you. Okay, thank you for your interesting lecture about historical nanomaterial, about synthesized nanomaterial, characterization, and nanomaterial beyond future perspective for advanced technology application. We hope that all participants could gain many new insight and knowledge for this lecture. Okay, if there isn't any question, will be the end of today's lecture. We would like to reminder to all participants for always check the announcement given. And for next lecture session, we'll have on tomorrow, Thursday at 8 a.m. That's all for this session, and thank you for participation. Assalamualaikum warahmatullahi wabarakatuh. Thank you for Dr. Akfiny.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Arun. Thank you all. See you.